Alright, let's go ahead and open up to page 157. Before break, we've been looking at all these different characteristics of graphs. We were looking at above x-axis, below x-axis, x-intercepts, multiplicities. We're going to dive a little bit more into end behavior today. We did, let's see, what are some other things? Ooh, concavity, that was kind of new for us. Points of inflection, maxes and mins, all that good stuff. But on 157, on our day before break, I think I had some of you fill out this chart, like just certain numbers, was that right? Okay, we're going to bring that all together today, that way we can have this chart filled out in its entirety, and then we're going to try to analyze this chart to see if there are any patterns that we can recognize. That way we can kind of make up some rules, perhaps, like when does an end behavior go up, when does an end behavior go down. So I forget who I assigned what, but I think we did 2 through 5 was over here. Okay. Sarah, can you give me number 2? What did you discover based on your calculator?
Even.
Okay.
Negative.
Okay.
Fall.
Fall. Okay, so as a refresher, before break, we were taking a look at these standard form equations. Okay, no parentheses, all the exponents are in order. And the first thing we looked at was what was the degree, meaning the largest exponent. In this case, that was a degree of 4, so that's an even number. We then took a look at the leading coefficient. Okay, what is the number in front of that x to the 4th term? And if you take a look at that based off the equation, we have a coefficient of -1. So it's a negative number. Then we graphed this on the calculator and you took a look at what's happening on the left side, what's happening on the right side. Sarah saw that the graph decreased or fell to the left, and it did the same thing on the right hand side. Okay, so we're going to fill out the rest of them, identifying those same characteristics. Anthony, do you think you can give us number 3? Even, negative, fall. Okay. Melissa, can you give us number 4?
Even, positive, rise.
Okay. And Tori, can you give us 5? That's the only one you didn't get. Okay. Rebecca, can you give us 5?
I can pick out my answer, but I can calculate it
Really quickly? Okay. Let's see. The degree is odd. We have a power of 3. The number in front of that term is like an understood number 1.
It looks like it's fall rise.
Fall, rise. Looks good. All right. So if you did not fill out 2 through 5 before break, you've got to make sure that you fill in those categories or those boxes. All right, next I think we had, was it 6 through 9 or 6 through 10? Something like that? Okay. Let's see, Emily, can you give us 6?
I got odd
Okay.
and positive, and then I didn't get to do the rise or fall because I did like the first 2 columns.
You did the first 2 columns, okay. Ashlyn, were you able to get the rise or fall for 6?
I got to 2 through 5.
Oh, you did 2 through 5, okay. Marie, were you able to get number 6, either the rise or the fall? Yeah, you weren't here, I'm sorry. Yeah. You got it now? You looked it up? Okay.
Yeah. I got rise for the left and then fall for the right.
I think it's
wait, that was for the number 7.
number 7, okay.
It was the fall for the left
Uh-huh.
and rise for the right.
Rise for the right, looks good. Okay. Let's see, Grace, were you able to get 7? Okay. Rise, fall, looks good. Okay. Rachel, were you able to get 8?
No, I stopped there because the bell rang.
The bell rang, okay. That's fine. Let's see. Maybe we'll check this out. Some of you might be able to do this real quick if you have a calculator available. We have an odd degree, okay, power of 5. The number attached out front of that is a -1, so that's a negative number. And if you were to graph it on your calculator, it would rise on the left-hand side but fall on the right. Did anybody get 9? Good, Marie? Okay. Yep. Rise and fall. Looks good. Okay. And did you guys have to do 10 as well? Did anyone able to get 10? You want to go to Marie?
Even degree.
Okay.
Constant coefficient.
Yep. Rise, rise. Good. All right. And then my last group over here, 11 through 14. Dylan, were you able to get 11?
Yeah, even, negative, fall, and fall.
Even, negative, fall, fall. All right. Brianna, were you able to get 12?
Only positive fall rise.
All right. Evan, were you able to get 13?
I got even positive, but I didn't get the rise and falls.
Okay. Can someone help him out with the rise or fall for 13? Yeah.
I got rise, rise.
Rise, rise. Okay. And Caden, were you able to get 14?
Odd, negative, rise, fall.
Looks good. All right, so make sure that table's filled out. All right, so once you have it filled out, I want you to take a look at it, try to find some type of pattern in there. There's a few of them that we're going to discuss, but I'm looking for kind of a general one that you might notice. What do you think, Tori?
Anytime it's on, like action to the left and the right will be opposite. Anytime it's even, will be the same.
Look at that. All right, so if you look at all these odd ones that we labeled, the end behavior were in opposite directions. So graphically speaking, one side of the graph went up, whereas the other side went down. Okay, or vice versa. Yeah.
For the odd ones, whenever the coefficient is negative, it'll end going towards a negative direction, or it'll go in a line.
Okay, so Tori's first one was kind of in a general sense. If it's odd, they go in opposite directions. If they're even, notice how they're both the same. Either they both fall or they both rise, okay? But maybe we can get a little bit more specific. Like what if it's even with a negative or even with a positive? Okay, so Tori was saying how if it's odd with a negative, she said it would end, like meaning the right-hand side of the graph, like you read a book left to right, it would end negative. So the right-hand side would fall, which means the left-hand side would rise because we have that opposite relationship, okay? What about an even connection? If you have an even degree with a negative coefficient or an even degree with a positive coefficient, yeah?
Well, if it has a negative coefficient, they will both fall.
They both fall, okay?
And if it has a positive coefficient, then that will rise.
There we go. Okay, so notice how this negative coefficient, that's kind of dictating perhaps what the right side is doing. Notice how negative fall, negative fall, negative fall, negative fall, negative fall, negative fall, negative fall. Okay, so the right-hand side is dictated by what the coefficient's telling you. What the left-hand side does is dictated by whether if it's even or odd. Okay, is the left-hand side also going to fall if it's an even degree, or is the left-hand side going to rise if it's an odd degree? Okay, so we're going to kind of make note of all those connections or relationships on the next page. Okay, so we're going to have the general ones up top, and then we're going to have kind of the more specific ones in the table, because it's those specific ones that are a little bit more accurate or concrete. Those are the ones that we're going to use. So first off, Tori's kind of general connection here was if the degree was odd, the end behavior were opposites, meaning one side rose while the other side fell. But if the degree was even, the end behaviors were the same, meaning they both rose on the left and the right, or they both fell on the left and the right. Can you guys read my chicken scratch? Okay, so we're going to go ahead and list these kind of four possibilities, these four kind of more concrete or specific relationships. We had one case where we could have an even degree and a positive leading coefficient, or maybe we have an even degree with a negative coefficient. But what if we had an odd degree with a positive coefficient and an odd degree with a negative? Okay, these are our four instances. So if we had an even degree with a positive leading coefficient, what do you think the left and the right end behavior would be without even looking at a calculator? What shape or what type of end direction would our graphs have? Yeah. There we go. Okay, so this is how I would think about it. The fact that we have a leading coefficient that's positive means that the right-hand side is going up. I would kind of always start there. But the fact that it's even is also telling us that the degrees or the end behavior should be the same. So if this was a rise, then this should be a rise as well. All right. So for number 2, if our leading coefficient is negative, the right-hand side's going to fall. But the fact that we have an even degree means that the end behavior should be the same. So the left-hand side is going to fall as well. So I would always use the positive and negative to help you with the right-hand side, and then the even or odd to help you fill out the left. Does that make sense? Okay. Let's go ahead and try the next one. We have a positive leading coefficient, so the right-hand side will rise, okay, go up, positive direction. But since we had an odd degree, we know that the end behaviors should be opposite. There's that O idea, like odd and opposite. So this left-hand side should fall. And for our last one, we have a negative coefficient, so it's going to fall on the right. Odd degree means opposite on the other side, so it's going to rise on the left. I don't want to say we need to memorize these, but do you see a pattern within them that you could use to help you remember them? Okay. So what we're going to do is we're going to start to incorporate this end behavior in our graphical analysis. So we're going to look at high points, low points, concavity, but now we're going to analyze what's going on the left-hand side and the right-hand side of a graph. So let's see if we can complete some of these characteristics for the graphs at the bottom. So we have a function. We're going to identify the zeros and multiplicities. Nothing new for us. The degree and the type of function. So what is the name, meaning like cubic, quartic, linear, quadratic. What would you classify this graph as? And then we're going to determine if the leading coefficient of the equation is positive and negative and justify how you know that. So we have no idea what the equation is of this graph. Okay, but maybe we can start to pick apart the graph to help us write some type of an equation. We don't know what it is exactly, but maybe we could write a possible one. So based off this graph, can we list some zeros, some x-intercepts? Yeah. -3 and 1, okay. And based off the graph at those x-intercepts, can you describe their multiplicities? Yeah. There we go. All right, so a multiplicity of 3, we have that kind of level graph shape on the x-axis. Multiplicity of 1 goes straight through, or it strikes through the x-axis. Looks good so far. What about the degree or the type of function that this graph is? Yeah. How did you know?
There's 3 bumps in the graph,
Okay, good. So you can look at two different things. Graphically, if you look for those humps and bumps, we know we have kind of one hump towards the top of the graph. The other two are a little trickier to find. They're actually the humps on either side of the multiplicity of 3. Those are ones that are a little tricky. So we have 3 humps or bumps, so the degree is 1 more than that, which would be 4. Or if you can identify the multiplicities and add them together, that's another way you could determine that. So 3 plus 1 would give us 4. So if it's a degree of 4, what name do we classify this graph as? Yeah. Quartic, right, like quarter. All right, perfect. So let's go ahead and try to think about what is a possible equation, okay, for this graph. And before we get there, let's go ahead and talk about kind of the leading coefficient. Can you determine what the leading coefficient might be? We don't maybe know what the number is out front, okay, because if you take a look at this table, you don't have to flip if you don't want to, but if you take a look at this table, this leading coefficient was 2, this leading coefficient was -1, this leading coefficient was +1, we have -2. Okay, we might not know what the number is, but maybe we could figure out what the sign is. What do you think, Marie?
Would it be even negative?
Okay, so we know the degree is even, right, because we said it was 4. And why is the leading coefficient negative? All right, notice how on both sides, okay, if it's an even degree, both sides are doing the same thing. They're both going up or they're both going down. The fact that they're both going down is signifying we have that negative number out front. So if you take a look at your chart up here, we already knew we were dealing with either option 1 or 2 because we had a degree of 4. But since the graph is falling on both sides, we know we have that negative leading coefficient. Okay? Actually, you only really have to take a look at the right-hand side to help you determine that, because we use the left or the leading coefficient to help us determine the right end behavior, and then the degree to help us figure out the left. Okay, so negative because we'll say the right end behavior is falling. All right, so with this information, the fact that we can identify the x-intercepts, we know the degree, the multiplicities, the leading coefficient, we're going to go ahead and write a possible equation. Okay, and it's going to be easier for us to do it in factored form, like using the little parentheses. None of the ones that we had on the front page were in factored form. Okay, these are standard, no parentheses, exponents all in a row. But to help us in a general case, we're going to use parentheses here. So can we fill in some of the factors of the graph? What information can we use to help us with the factors? Yeah.
We can use the zeros to make factors.
There we go. So if we have a 0 of -3, what would the related factor be? Yeah. X plus 3, okay. And then if we have a 0 of 1, the related factor would be x minus 1. All right, so we use the zeros to get the factors. Where do the multiplicities kind of come into play in the equation? Yeah.
Well, that would be the power, like how many times that factor would show up in the equation. So it would be to the third power.
There we go. So if you were to actually write out x plus 3, x plus 3, x plus 3, okay, you would have it 3 times, but you can simply rewrite that as a power to the, or a power of 3, because they're all being multiplied together. Same thing with the 1. You don't have to put a power of 1 there, okay? If you don't write it, it's kind of understood to be a 1. That's completely up to you. Okay, so the zeros help with the factors, the multiplicities help with the powers. Notice how 3 plus 1 is giving us that degree of 4, which is checking out, but somehow we have to make sure we have a negative coefficient out front. So in front of this first factor, we're going to throw in a negative sign because the end behavior is signifying we have a negative coefficient. So in front of the first factor there, bless you, we're going to put a little negative sign. Now what you could also put there Okay, I'm not saying you have to do this, but you could also put a variable. Okay, we'll say maybe letter A. That A might be representing some other number. Maybe it's a -2 out front, maybe it's a -1 out front, maybe it's a -5 out front. We don't really know what the number is, but we for sure darn know that it's a negative, okay, based off of that end behavior. Okay, so I'm not saying you have to put the A there, but there might be some number out front that would give us this graph specifically. Okay? Do you think you guys can try the next one? Based off the graph, identify the zeros, multiplicities, degree, leading coefficient, and then bring it all together to write an equation. All right, any takers on the zeros and their multiplicities based off that graph? Good, Marie? And 1, okay. 1 and 2, looks good. All right, so based off of either the graph or those multiplicities, what was your degree? Yeah? 3. So what would we name that as? Cubic, good. Okay, what about the leading coefficient? If we were to write an equation, do we have a positive number out front or a negative number out front? Yeah. How? Did you know? Yeah. The right end behavior is falling, good. All right, so we're going to bring all of that together to write a possible equation, okay? So we're going to start off with our factors based off of those zeros and then go from there. Any takers? Give it a shot. Yeah. Okay. Powered by 2. Perfect. How did you do? Pretty good? Okay, remember this is a possible equation because we don't really know what that A value is. Okay, it could be anything at this point. We would need a little bit more information to help us figure that out, but at least this is some type of an equation to put us on the right track as to what this equation would be for this graph. All right, you guys on a roll? Do you think you can do 2 more? If you take a look at the next page, they're very similar. any takers on the zeros and multiplicities for the first one? Yeah.
Negative 3, 1, and 2.
1 and 2. Okay, and their multiplicities? 3, 1, and 1 looks good. Alright, so based off that, can we determine the degree? What type of function? Yeah.
5.
Degree of 5, so what's the name?
Quintic.
Quintic, good. Okay, and then what about the leading coefficient? If we tried to write an equation, would our first number need to be positive, negative? Yeah. How'd you know? The what? Which side? The right side, yep, because the right and behavior is falling. Okay, so we're going to bring it all together to write a possible equation. Any takers? Yeah?
Negative a parentheses x plus 3 cubed,
Okay.
x minus 1, and then
X minus 2. Perfect. How'd you guys do? 2 thumbs up? Way up? All right. What about the next one? Any takers on zeros and multiplicities? Yeah.
negative 2 and 1.
Okay, multiplicities? 3 and 2. All right, so what about our degree? Based off those zeros and multiplicities? Yeah. So the name? Quintic again, okay. So both of these are quintic graphs, but notice how they kind of look completely different, right? They're different shapes, but they're the same type of graph. So what about leading coefficient? Yeah.
Positive.
How'd you know?
Because the right and behavior is rising.
There we go, because right and behavior is rising. All right, so possible equation. Any takers? Yeah.
Would be a
Positive
positive,
A, yep, okay.
x plus 2 powered by 3,
Yep,
and then x minus 1
powered
powered by 2.
by 2. How'd you do? Wonderful. All right, so we're going to take a look at the same concepts, okay, the same types of questions, but this time instead of basing our analysis or answers off of a graph, what if we were given a table? Okay, so instead of a picture, we have this chart information. So they give us some directions at the top. The table below is a polynomial function, okay, some type of roller coaster graph. The zeros in the table are the only zeros of the function. Okay, so the only x-intercepts. There aren't any hidden ones in there that we're not aware of. Okay, so they're giving us the x-intercepts exactly. And none of those x-intercepts have a multiplicity greater than 2. So the multiplicities are either 1 or 2. Okay, no level spots of 3. Answer the following questions. All right, so based off the table, can we determine what the right and left sides of the graph would be doing? Even though we don't have a picture, can we still analyze the numbers to help us figure it out? Yeah.
Would be fall and rise.
How'd you know? Yep, fall and rise.
Because the left function is a negative.
Yep.
And the right function is a positive.
There we go. So notice how as you travel to the left, the numbers are getting more and more negative, so you're falling. As you travel to the right, the numbers are getting more and more positive, which means you're rising. So we'll say the left-hand side falls, whereas the right-hand side rises. So based off that end behavior, can we determine what the degree of the function might be, like cubic, quartic, quintic, and what about the sign of the leading coefficient? Do we have a positive first number or a negative first number? What do you think based off of the left and the right sides? What do you think, Marie? Say it again.
Or are you asking?
Just in general, is the degree like even or odd? We'll get to what the degree is more specifically in a second, but what can you say about the degree? Is it even or odd? And then the sign, is it positive or negative? Yeah.
Is it odd positive?
How'd you know?
Because the right and behavior rises to positive,
Okay, so we'll say positive leading coefficient because the right side rises. So when we get to writing the equation, we know we need a positive A or a positive number out front. And then Hannah, how'd you know it was odd?
Because the left and right is usually.
Right, notice how the left and the right side are opposite directions, okay? So we have an odd degree because the left and right sides, we'll say, are opposite. Okay, so at least we know in a general sense we have an odd degree and we have a positive first term, but maybe we can look at the table a little bit closer to figure out, well, what specifically is the degree? Okay, is it 3, is it 5, is it 7? It has to be something odd. Let's go ahead and check that out a little bit closely. So it says identify the zeros and the multiplicities, which if we can figure out the zeros and the multiplicities, we should be able to figure out the degree. Okay, kind of how we did at the tables at the top of that page. Okay, so can we identify where the zeros are based off that graph? Where the x-intercepts are? Yeah.
-3
How'd you get that?
since the y is 0.
There we go. Y value 0 indicates an x-intercept. Looks good. Okay, so those are the x-intercepts because y equals 0. And then can we identify what the multiplicities are of each of those? So I'm going to go ahead and draw a little arrow here signifying the multiplicities. What do you think, Tori? How'd you know it's 1?
Because the y is positive, so it's
There you go. To the left side, you're negative. To the right side, you're positive. So at that x-intercept, you're traveling through the x-axis. You have that sign change, which is indicating either a 1 or a 3 multiplicity, but they told us none of them are greater than 2. So this one would have to be a multiplicity of 1. Okay. And then what about the multiplicity for the x-intercept of 1? Yeah.
It is 2.
How'd you know?
Because you should follow the opposite sides. It's rising, or it's like falling and rising, hits it.
Oh.
We know it's not.
Exactly. There's no sign change in there, so you're not going through the x-axis, you're just touching it or kind of bouncing. So that's our multiplicity of 2. All right. So for this one, it says justify your answers. We'll say that there's a sign change, okay, for that multiplicity, and maybe no sign change for that multiplicity. All right. We're going to add a fourth question in here. I'm not sure if you guys have room or not, but we're going to label this question D. Okay. We're going to write the equation. Okay, not a equation. Do you see the difference between the two? A equation is signifying some possible equation, like something generic. Right, the equation means the exact. Okay, so we're going to actually figure out what that A value is in this case. Let's go ahead and start out with the generic equation. Do you think we can go ahead and fill in the factors like we did on the other ones? You want to give it a shot? Yeah.
Would be positive
Okay, positive A.
3 plus, x plus 3
Yep.
powered by 1.
Powered by 1. Okay.
X minus 1
Powered by 2. All right, so that's the generic equation, okay, where you don't know what that A value is. But the fact that we have a table of values and we know some specific points on this graph might mean we could use that information to help us figure out that A value. What is that positive number out front? Do you have any ideas how we might use the table to help us figure out that missing point? Yeah.
Since we know one of the x's and one is all the x's.
Okay, so we're going to pick a point. You specifically said 1. Like you want to use this point right here?
That, yeah, that or the negative.
Okay, well, here's the thing. If you use these, if you use either one of these, if you plug in 1, isn't that going to make this factor 0? So if this is 0 times this, wouldn't that make it, the a go away? Okay, so we use the x-intercepts to help us write the factors, but we have to pick some other point in the table to help us figure out the a value, because either of those factors is going to make the a disappear. So between all the other options, which point might you want to use? Yeah. Okay, it might seem like a big number, okay, but we're going to pick any other point, and notice how this 6 is representing an x value and the 225 is representing a y value. So we're going to substitute in those numbers for x and y. This 225 we can put in for f of x, because remember f of x and y are the same thing. And we're going to go ahead and substitute in 6 for all the x's. Now if we did that, we would have 6 plus 3 and then a 6 minus 1 squared. So you may need a calculator for this to eventually help you figure it out, okay, because our numbers might get a little large. But let's go ahead and figure out this coefficient out front, because after we plug in the x and the y, notice how the a is the only variable we have left. So we have, let's see, 9 times 25. Can someone help me out? Is it 225 exactly? Alright, so to figure out what a is, divide the 225 over. What's our a value? A is 1. Okay, so in the end, instead of having plus a out front of this generic equation, we could simply, I'm running out of room here, I'm going to write it over here. Our actual equation, okay, the equation that would give us this exact table, we would have a coefficient of positive 1, and then the x plus 3 and the x minus 1 squared. Okay, so you can figure out that coefficient number when you have a table of values. It's a little trickier when you have a graph. Okay, I'm going to slide up the paper just for a second. When we had these graphs here, the only true points we knew were the x-intercepts. Okay, they don't really give us another point on the curve to help us figure out that a value, right? So in these cases, we weren't able to figure it out. That's why we just left it there. But since we do have more points, more information, we can use that to our advantage to help us figure out that leading coefficient. Yeah.
How does the graph have an odd degree if the highest
Good question. Okay, so when you take a look at this equation we wrote, this power is 2 and this power is 1, right? These powers are signifying the multiplicities. When it's in factored form, like those groupings, these are representing multiplicities. So when you add them together, that gives you your degree, okay? If it was in standard form, like these ones, you see how there's no parentheses? Then it's just the highest powered. There's a difference between the two, okay? That's a good question. We doing okay? So far so good? Left and right end behavior not too bad? Alright, let's not lose it because we're going to do another graphing or table example tomorrow, and then we're going to get into the good stuff. We're going to give you an equation and we're going to graph it by hand. No calculator necessary.